So we're doing another problem by Rosen in discrete mathematics and its application. We're going to prove by induction that the square of odd integers is equal to this mess over here. I forgot to put over 3. All right, so we're going to do this by induction, which means we have to set up a base case. Now the problem asks for non-negative integer. So n is a non-negative integer, which is a fancy way to say that n is 0, 1, 2, ... Or n is a natural number with 0. So that means that we start the base case at 0. So we're going to say n equals 0. And we're going to see if the left-hand side is equal to the right-hand side. As usual, induction on equalities like this, we're going to prove the left and right-hand side are the same. So we're going to substitute n equals 0 on the left-hand side, and we'll do it for this term here. You could think of n equals 0 as being the first term, the 1 squared term, or you can think of it as being that 2n plus 1 squared, where n is 0. So those will be equal to 2 times 0 plus 1 squared. That's equal to 0 plus 1 squared, equal to 1 squared is equal to 1. Now the right-hand side is this n plus 1, 2n plus 1, 2n plus 3, divided by 3. So we're just going to substitute 0 for n. Again, this is like saying the first term on the left is equal to the first term on the right. And we're substituting. Now we're mathing. 2 times 0 is 0. 2 times 0 again is 0. Then we get 1 times 3 divided by 3 is equal to 3 over 3 is equal to 1. So indeed, the left-hand side is equal to the right-hand side. And I'm erasing. So the left-hand side and right-hand side are the same, which means the base case holds. Now we're going to do the inductive step. I'll just write that down. The inductive step, we're always going to establish an induction hypothesis. We're going to swap the n's in our original statement with k and assume that this is going to be true up to some value of k. So in other words, we're going to say 1 squared plus 3 squared plus 5 squared plus ... plus 2k plus 1 squared will be equal to k plus 1, 2k plus 1, and 2k plus 3 divided by 3. So we're going to assume this is true. In your proof, you can write that so you don't forget. I like to write IH because this is the induction hypothesis. In these cases, when we're proving something by induction, we're always going to be using the induction hypothesis. If you get through your proof and you realize you haven't used it, you probably did something wrong. So remember this. So I'm going to use IH here. So induction, we want to prove that the next term is true, or the k plus 1 case is true. Let's write this here. Here's what we want to show. That the k plus 1 case is true. So we're going to replace k's in the right-hand side with k plus 1s, and on the left-hand side, we're going to add the next term. In this case, let's write it. So the left-hand side will be 1 squared plus 3 squared plus 5 squared plus dot, 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 plus 2k plus 1 squared plus 2. Now I'm replacing this with the next term, which is the k plus 1 term. So we're thinking of integers, k plus 1, k plus 2, k plus 3. And so on the left-hand side, replacing k plus 1 in the last term, we get the sequence of integers, odd. Now the right-hand side is going to be a little ugly because I'm going to replace k with k plus 1 in every case here. So k plus 1 in that first term, 2k plus 1 plus 1 in that second term, and 2k plus 1 plus 3 in that third term. So again, this is the k plus 1 case. We want to show that these two things are equal. Let's clean it up a little. So what we're trying to prove here is this. We're trying to show that 1 squared plus 3 squared plus 5 squared plus dot, 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 plus 2k plus 1 squared. Now I'm going to simplify this term by distributing here. So that's 2k plus 2 plus 1. So the inside is 2k plus 3. So that's the next term is 2k plus 3 squared. Now we're going to clean up the right-hand side mess. The first term here is just k plus 2. We distribute this, we get 2k plus 2. So then we get 2k plus 2 plus 1, which is 2k plus 3. We're going to do the same thing here, distribute 2. We get 2k plus 2 plus 3 is 2k plus 5, all divided by 3. So our goal here is to show that, forgive me, keep hitting this eraser button, that 2k plus 3 times 2k plus 5 divided by 3. So this is what we want to show. We're not entirely certain that this is true. So what I'm going to do here is put a little bit of question mark because I don't know that the left-hand side and the right-hand side are the same. That's exactly what we're trying to show. Now in these proofs, you're generally going to pick a side and then algebraically show that it's equal to the other side. Usually in these cases, we're going to pick the left-hand side. We're going to pick the sort of summation side. So I'm going to pick the left-hand side and show that it's the same as the right-hand side. Then we get 2k plus 1 squared plus 2k plus 3 squared. Now, I'm going to group it like this. I'm going to group the first k terms, which remember is just the original statement with the k replaced. And I'm going to leave this guy outside. This is the last term, the k plus 1 term. We're going to notice here that this is the induction hypothesis that we set up earlier. We said that 1 squared plus 3 squared plus 5 squared all the way to 2k plus 1 squared is equal to k plus 1, 2k plus 1, 2k plus 3 divided by 3. We assume that is true for all values of k greater than or equal to 0. So we're going to use that. We're going to replace our parentheses here with the, let me make sure I write it down correctly, k plus 1, 2k plus 1, and 2k plus 3 divided by 3. And don't forget this last term here. I'm going to say this is true by the induction hypothesis. So that's what I mean in the beginning when I said if you haven't used your induction hypothesis, you're probably making assumptions you shouldn't have. And your proof is probably going to be incorrect. All right, so we're still on the left-hand side, and our goal is to make this look like the right-hand side. So what we're going to do now is some algebra. The first thing we want to do is add this. So if I add these two terms, that means I have to get a common denominator. So that means that I'm going to be multiplying the second term here so that we have a 3 So we're multiplying the top and bottom by 3. The professor once said, always write 1 as 3 over 3. He said that for anything that was needed to find a common denominator. So now I can add these two things, right? I add the tops and I keep the bottom as a single denominator. So we're going to add this. So this is 2k plus 3 squared divided by 3. So all we really did is consolidated the top. We have a common denominator, 3. And so now we can start looking at some algebra here. So we noticed that in the first top term, there's a 2k plus 3, and then we're adding that to 3 times 2k plus 3 squared. So let's factor out a 2k plus 3. Keep hitting this erase button. So 2k plus 3 term we're going to factor out, and a 3. I always think of this as where I want to end up, because we know we want to end up. We want to end up precisely here. We want a 2k plus 2, 2k plus 3, 2k plus 5 divided by 3. Well, that's not 2k. That should be k plus 2. My fault. It should just be k plus 2. All right. So what's left? K plus 1, 2k plus 1. Now we factored out a 2k plus 3, so let's just think of that as 1 plus 3. And then we have 2k plus 3 left over. So far, so good. I hope you're following the algebra. Now, anything times 1 is itself, so that's sort of redundant. So now I'm going to FOIL this guy. First, outer, inner, last. Let's write this term so we don't forget it. So 2k plus 3 divided by 3. And the foiling, we have 2k times k is 2k squared. K times 1 is k. 2k times 1 is 2k. And then 1 times 1 is 1. And then we're going to add that. We're going to distribute this. So this becomes 6k plus 9. So we're still rolling here. 2k plus 3. And I kind of want to separate that. So when we get to the point where we're going to combine stuff, we can see what's going to happen. So it's combined like terms here. We have a k, we have a k, we have a k, and then we have a constant. There's no pairing for k squared, so we're just going to write 2k squared plus we have 6k plus 2k is 8k plus 1k is 9k, and then 9 plus 1 is 10. So then we have this polynomial. So I want to factor this polynomial in 2 binomials. So again, if you remember your algebra, conceivably I should be able to write this as 2 factors. What I do is I look at the first term and think to myself, what do I need to get 2k squared from? Well, 2k times k will give us 2k squared. There's really no other options. And then I think of 2 terms that multiply, that can be 10, 5 and 2. That works out nice. Now I'm going to put it, let's just put it here and see if we're right. So to check it, I'm going to FOIL. So first term's 2k squared, 4k, 5k, add that up to 9k, 5 times 2 is 10, all positive. So that's it. So now let's distribute this back, essentially multiplying it out. So we get 2k plus 3, 2k plus 5, k plus 2 divided by 3. If we do a little rearranging, so put that term first, put this term second, put this term last, divided by 3, we will notice that this is the right-hand side that we're looking to get. Way up here in the beginning. 2k plus 2, 2k plus 3, 2k plus 5 divided by 3. All right. So this means that the left-hand side is equal to the right-hand side, and that we are done. we've proven, so we can say QED. I'll use boxes and say our proof is done. So in fact, it is true that 1 squared plus 3 squared plus 5 squared plus dot 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 plus 2n plus 1 squared is equal to n plus 1, 2n plus 1, and 2n plus 3 divided by 3. That's it. That's the proof by induction. This dot 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 should hopefully you remember that these are just a bunch of terms between. All right, so that's it. That's the proof. If there's anything you would like to see from this or explain better, just leave a comment or email.